Hello everyone, I'm Zhang Lin from Sun Yat-sen University. Today I'm going to present our paper Collaborative Static and Dynamic Vision Language Streams for Spatio-Temporal Video Grounding. To begin with, I will give an overview of our work. In this work, we focus on spatio-temporal video grounding task. It aims to localize the target object both spatially and temporally according to the given text query. In this task, static cues like object appearance and dynamic cues like object motion are both important. In this work, we propose a collaborative two-stream framework. It contains a static and a dynamic vision language stream to perform cross-modal understanding on the static and dynamic cues, respectively. And we design a novel cross-stream collaboration block between the two streams to exchange reciprocal information for each other, and enable collaborative reasoning of the target object. Our method achieves new state-of-the-art performance. In the following, I will introduce our work in detail. In STVG task, given the input query text and the video, the model should predict the starting and ending time of the target moment that best match the query sentence. Like here, from 9.12 seconds to 14.84 seconds. And for each frame inside the target time span, the model should also predict the spatial bounding box of the target object. In this task, static visual cues like appearance are important to distinguish the target object from other object that occurred in the same frame. For example, in this case, the text query is "the man in the red stripe goes to the sofa and turns." Here, if the model can understand red stripe, then it can distinguish the target man from other persons. Dynamic visual cues like human action are also important for achieving accurate temporal boundary prediction. In this sample, the model needs to understand the action "goes to the sofa and turns," so that it can precisely predict the temporal boundaries. Thus, understanding both the static and the dynamic visual cues described in the text query is essential for the model to achieve precise predictions. In this work, we develop a framework that consists of a static and a dynamic vision language stream, to perform static and dynamic cross-modal understanding respectively. The architecture of our proposed framework is shown in this slide. It mainly consists of a static and a dynamic vision language stream. The static VL stream performs cross-modal understanding in a single frame, and it learns to localize the target object spatially, according to intra-frame visual cues like object appearances. It takes image frames as input, then an image encoder is used to extract frame-level features. After that, the frame-level features and the textual features are fused with a cross-modal transformer, then the fused features are inputted to the prediction head to predict the bounding boxes for each frame. Our dynamic VL stream performs cross-modal understanding across multiple frames. It learns to predict the starting and ending time of the target moment according to dynamic visual cues like human action. In the dynamic stream, we first extract clip-level features with a video encoder, then we develop a spacetime cross-modal transformer to learn spatio-temporal cross-modal dependencies. The features outputted by the spacetime transformer are used to predict the starting time and ending time of the target time span. In order to enable the static and dynamic streams to transfer useful and complementary information from each other, we further design a novel cross-stream collaboration block between the two streams. In the following, I will introduce the detailed architecture design of the cross-modal transformers and the cross-stream collaboration blocks. This slide shows the architecture of the transformers in the static and dynamic VL streams. The left part is the transformer in the static VL stream. It performs cross-modal understanding of static visual cues in a single frame. It first fuses the linguistic feature and the single-frame visual features with a transformer encoder, then in the decoder, following DITR, we use an object query vector to query the object localization information from the output of the encoder. At the last layer of the decoder, we use a 3-layer MLP to predict the bounding box. The right figure illustrates the architecture of the spacetime cross-modal transformer in our dynamic VL stream. It is designed to perform cross-modal understanding of dynamic visual cues like human action. The input to this transformer is the video features extracted by the slow-fast network, and the linguistic feature. In each transformer layer, we first perform self-attention for visual modality and language modality independently, then we use a cross-attention to fuse the information from the two modalities. When performing self-attention in visual modality, we split the spatio-temporal self-attention into a spatial and a temporal self-attention to reduce computation cost. Next, let's come to the cross-stream collaboration block. Our cross-stream collaboration block is proposed to enable the two streams to perform collaborative reasoning. Its architecture is shown in this figure. Here, the static block and dynamic block indicate a transformer layer in the static and dynamic stream, respectively. Our cross-stream collaboration is performed after each static and dynamic block. The collaboration is achieved by a static to dynamic and a dynamic to static information transmission block. In the following, I will introduce the design of these two information transmission blocks. The static to dynamic information transmission block is designed to help the dynamic stream focus only on the motion of the target object. Here, we use the attention map AI learned in the static stream. As shown in this figure, the attention map AI only attends to the person that best matched to the text query. In our static to dynamic information transmission block, we perform a Adamar product between AI and the feature FVI from the dynamic stream. This can help the dynamic stream to focus only on the motion of the target object, and neglect the motion of other object. In our dynamic to static information transmission block, the object query from the static stream first queries some text motion fused features from the dynamic stream. This helps the static stream learn some motion information from the dynamic stream. Then in the querying mixing block, we mix the information of object queries from different frames using a temporal attention. This helps the model track the target object for achieving more consistent grounding results across different frames. The above is the introduction of our method. Now, let's see the results. As shown in these tables, our proposed model achieved new state-of-the-art performance on HCSTVG and VID-STG datasets. It outperforms previous models by a considerable margin. And in this ablation study, the results show that the static to dynamic and the dynamic to static information transmission blocks both bring some improvements. And combining them brings a significant performance improvement of 2.3% mean VIAU. We also compare our cross-stream collaboration block to other designs, and the results further demonstrate that the proposed collaboration blocks can enable better collaboration of the static and dynamic vision language stream. Finally, let's watch a demo of the model predictions. That's all. Thank you for your attention.